So for this next example, I have a linear transformation from r cubed to r to the 4. So this matrix, this is a 4x3 matrix. So it sends a vector from the 3-dimensional space to the 4-dimensional space. And the first question asks me, what is the range of t? Well, the range of a function is basically asking what are the possible value of t of v. So this one is asking me what are the possible values. What are the possible values of t of v? Well, to do that, let's just find out. So my t, this is just the vector that we have up there. 1, 2, 3, 4, 5, 6. I mean not vector, a matrix. 7, 8, 9, 10, 11, 12. What about the v? Well, this v is just a vector, so it's a 3-dimensional vector, and that makes sense because I can only multiply this matrix with something of dimension 3. So I multiply this matrix with something of dimension 3. So I'm just gonna call the 3 elements A, B, and C here. Now, if I were to multiply this out, okay, let's see what I'm gonna get. I multiply 1 by A, 2 by B, 3 by C, so I get 1A plus 2B plus 3C. You can actually go on. It's just a pretty easy multiplication, but let me actually just say that you can actually write this big vector as a sum of 3 vectors. This big vector thingy here is actually going to be just 1, 4, 7, 10. So this is the first column of my matrix T times A plus 2, 5, 8, 11, which is the second column of my matrix. I mean, not 11, which is just the second column of my matrix. 2, 5, 8, 11 times B plus the last column, which is 3, 6, 9, 12 times C. Okay. So this is the same kind of thing that we see in the previous example. Notice that in the previous example, I want to compute t of A and B, and it turns out to be just A times the first column of my matrix plus B times the second column of my matrix. So same thing is kind of happening down here. The image of ABC is just A times the first column of my matrix plus B times the second column plus C times the third column. Now my A, B, and C can be any real number. So A, B, and C can be any real number. So I need to find out what are the possible values for this whole guy. So I need to find out what are then all the possible values for this terms here. So I need to find out what are the possible values of this guy times A plus this guy times B plus this guy times C, where A, B, C can be any real number. It turns out, well, we talked about this already. This whole thing is actually just gonna be all the linear combination. All the linear combinations of the 3 vectors that we see here. It's just all the linear combination of 1, 4, 7, 10 and 2, 5, 8, 11 and 5, 6, 9, 12. I mean not 5, 6, 3, 6, 9, 12. It's just the set of all linear combination of these 3 guys, actually just the span of these 3 guys. So it's just the span of this 3 guys. It means same thing. Now there is another name for it. Another name for it is, this is called the column space. We talked about this in the last lecture. In fact, we actually have done the example on this. We actually have already found the column space for this matrix. We did this in an example 6.2. And we actually already found this out. We knew that the all the linear combinations of this tree guy, the span of this tree guy is just gonna be the span of the two vectors here. So that's gonna be 1, 0, negative 1, 2, and then 0, 1, 2, 3. So I actually take this answer straight right from example 6.2 from last time. Another thing that I like to point out is that this corresponds to the last bullet that we have up here. So given a linear transformation that is multiplied by the matrix A, the range of T is the column space of, well, this is a typo actually. The column space of the range of T is the column space of my A. So I'll fix this. So that's for my part A here. The range of my linear transformation T here is just the column space of my matrix here, and we actually already have found that out. Now let's do part B. I'd like to find all vectors v such that tv equal to 0. In other words, I need to solve for v such that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I multiply this to the vector ABC and set that equal to 0, 0, 0, 0. Notice the dimension because this is again a 4 by 3 matrix. 4 by 3, yeah, that's right. So now I need to solve for all the ABCs that make this matrix equation came true. And, well, we actually also already did this. This thing actually has a name. The space for all the ABC that makes this happen is called the null space of the matrix. And we actually also already did this in the last lecture. We did this in example 6.1. So once again, I'm just gonna go ahead and just write down the answer for this guy. All the vectors v such that tv is equal to 0 is just gonna be just the span of this one single vector. So it's just a linear multiple of this guy here. 1, negative 2, and 1. So that's for my example 7.2 here.